Hello, dear students. Welcome to the lecture and welcome to the channel, and very welcome to this playlist in which we are discussing about different type of transforms which are used to move from time domain into the frequency domain. So up until now, so far we have discussed about Laplace transformation, Fourier transformation. We have discussed about the LTI systems. We have discussed about Fourier transformation and Laplace and how they function, their properties, uh, their values in detail. We have discussed the inverse Fourier and inverse Laplace transformation and even the relation between both of them. We have seen bunch of examples, numericals related to both of them, and then we have started discussing about Z transform. We saw what is a Z transform, why it is required, and what is the ROC of Z transform. In previous class, we have also visited the properties of ROC in the ROC of Z transform, and today we are going to discuss about the properties of Z transform itself. So if you have not checked out previous class, don't miss out the action. Watch the previous lecture, which is about properties of ROC, and then after that come back here and see this how the properties of Z transform takes place. Now if you have seen previous videos and if you are following this playlist for a long time, then you will find this today's video very simple, very satisfying. The reason is, so if you have followed previous videos, this is going to be a cakewalk for you because we have earlier discussed the Fourier properties, the properties of Fourier transform in detail with proof, and the properties of Z transform hold so much resemblance with it that you can only just see and say what will be the Z transform of this function. So without further ado, let's get started with the first property, which is none other than linearity property. And here you are. So what does linearity property tells us? So it is same old superposition theorem. It tells us um, whatever signal, whatever discrete signal and its Z transform satisfies the superposition theorem, that signal will be a linear signal. Let's see how. Let's say if I'm having a signal x1 of n and the Z transform of that signal is x1 of z. Same ways for x2 of n, and Z transform of that will be x2 of n, and the ROC for x1 of n will be ROC of x1 of z will be between the point a1 and b1, and ROC of x2 of z will be between point a2 and b2. So what will be the linearity property? So it will state us, whenever I take a1 into x1 of x1n plus a2 x2n, and whenever I take the Z transform of this cumulative function, the Z transform will be equal to a1 into x1 of z plus a2 into x2 of z. So basically it is telling us that whenever we take constant with my different functions who are having Z transform and we add them, we will get same constant in multiplied with the Z transform as well. So how does this property holds up? Let's see. Let's try to find it out. So see here on the left side, you can see x of z is equals to summation n is equals to minus infinity to infinity x of n z raised to minus n, which is equals to summation of n is equals to minus infinity to infinity the function, our function which we stated here, into z raised to minus n, because that is the value of x of n here, right? And the function here is the formula of my Z transform. If you haven't seen the previous video, this is the formula of Z transform. Then what we can do, we can write this summation and this z raised to minus n into this bracket, right? Or basically we can break the bracket, and what we will get summation n is equals to minus infinity to infinity a1 x1 n z raised to minus n plus summation n is equals to minus infinity to infinity a2 x2 of n z raised to minus n. Now what we can do, we can take constant values outside the bracket or outside the summation. So we will take a1 and a2 outside the summation, as both of them are constant values. And then what we will have inside the summation, see, isn't it the formula for Z transform of x1 of z and x2 of z, right? So instead of it, we will write x1 of z and x2 of z, and what we will get? We will get a1 x1 of z plus a2 x2 of z. And hence, your linearity property has been proved. Now see the next one, it is time shifting, or it is also sometimes called translational property. So what does it tell us? It says whenever we take Z transform of a discrete time signal x of n, and it is having the Z transform of x of z, and its ROC is between the points R1 and R2, then if I enhance my signal, if I make changes to my signal, instead of x of n, I subtract my signal from k. So if I take x of n minus k, and when we take the Z transform of that signal, the Z transform will be z raised to minus k x of z, and the ROC will remain same. There will be no change in my ROC. Now how does that happen? Let's see the proof of that. So let's say I'm having a signal x of n minus k, and I'm taking Z transform of my signal. So the summation of Z transform, the formula of Z transform will look something like this. Summation n equals to minus infinity to infinity x of n minus k z raised to minus n. Now let's say n minus k is equals to m. So this term will become m, and because we are taking x n minus k is equals to m, then n will become m plus k. So instead of minus n, we can write minus m plus k, right? And also the limits of my summation will become minus infinity to infinity, same as it was for n, but this time my m will go from minus infinity to infinity. Now see, if I break this bracket, can't I write z raised to minus k into z raised to minus m? So we are going to do exactly that, and we can take this z raised to minus k outside the summation, as the summation has nothing to do with x raised to z raised to minus k. We will have this term into the summation. Summation m is equals to minus infinity to infinity x of m z raised to minus m. And these two terms, isn't it the Z transform of my x of m, right? So the term will be z raised to minus k, which was left earlier, into x of z. So hence we have proved this property as well, and this property was time shifting or translational property. Next property is the scaling in the Z domain, which is very popular. It is sometimes also called multiplication by exponential function, and we use it very often as well. So it states that whenever we have a discrete time signal x of n, and we take Z transform, the Z transform of my x of n is x of z with region of convergence of point between points r1 and r2, then if I multiply a constant a raised to n with my discrete time signal, and then I take the Z transform of that signal, the Z transform will be equals to x of z divided by that constant a. And this time, as I was multiplying that constant with some power with my discrete time signal, the ROC will also get multiplied by that point, right? So ROC, if my ROC region of convergence for my Z transform was between point R1 and R2, so this time it will be between point A into R1 and A into R2. Now let's see the proof of it. So see, I'm taking Z transform of my signal a raised to n x of n, and I simply wrote the formula of it. Now instead of this a raised to n, if I take this a raised to n with my z raised to minus n, can't I write a raised to minus 1 or a inverse into minus n, right? The thing is still the same, right? Minus minus will become plus here. So I can write it this way as well. So when I write it this way, see what did it became? it actually became Z transform of the function A inverse into Z, right? So it will be x into A inverse into Z, and A inverse can be written as x of Z divided by A. So what is happening? See, because the function itself became Z divided by A, so region of convergence is still the same for the function Z divided by A. But if I want to find the region of convergence for only point Z, what will happen? For only point Z, for only my Z transform, my region of convergence will differ. This A will get multiplied with both of the radiuses R1 and R2, and the final region of convergence for Z transform, we will have A into R1 into A into R2. Now let's see another one. This one is called time reversal. So in time reversal, what do we do? If we take the Z transform of my discrete time signal x of n, and if Z transform is x of z, and with ROC between point R1 and R2, then whenever we take the Z transform of x raised to minus n, x of minus n, the Z transform will be x of z inverse. And not only that, but ROC of this signal will also differ. So this time ROC will become 1 by R2 less than Z less than 1 by R1. Now let's see how. Let's put this equation, put this signal x of minus n in the formulation or in the formula of Z transform. Now remember, we took n is equals to minus m. So instead of minus n, let's take m. And here also z raised to minus n, we will take z raised to m. Now because we are taking z raised to m, the limit of summation will also change. It will become infinity. Instead of minus infinity to infinity, it will become infinity to minus infinity, because we are taking n is equals to minus m. So what do we have to do in order to change the limit? We have to multiply with minus inside the bracket, inside my summation, right? So what will happen? To change this limit from infinity to minus infinity to minus infinity to infinity, what we will do? We will simply change the limit with x of m z inverse into z raised to minus m. So see, we are not making any changes in z as well, right? Now see this, isn't it the z transform of z inverse, right? See, we are having z inverse x of m and z inverse raised to minus m. So it is z transform of x of z inverse, right? Instead of x of n, we are having x of m here. And as it was z transform, so we can write it other way, the ROC 1 by z. And when you turn that equation around, what you will get? You will get this one, 1 by R2 less or equal to z less or equal to 1 by R1. That will be the region of convergence for my time reversed signal. Now let's see the differentiation in Z domain, or the multiplication by the ramp function is also called the same. So again, here what is happening? We are having a signal and the discrete time signal x of n, the Z transform of that signal is x of z with ROC R1 less than z less than R2. And when we multiply the same variable or the same sample point with my signal, let's say n, then the Z transform will change. What will be the Z transform this time? It will be minus z d by dz x of z with no changes in my ROC at all. So how does that happens? So let's see. Let's take the Z transform of x of n, and then we will multiply then we will multiply n with it. Or we can go reverse as well, right? From this one we can prove this one as well. So let's go reverse this time. Let's take x of z you know what is the formula of x of z, right? It is x of n z raised to minus n, and then we will take the differentiation of it. So what you will get, you will get summation of n is equals to minus infinity to infinity d by dz x of n z raised to minus n, and that will be equal to summation n equals to minus infinity to infinity x of n d by dz z raised to minus n, because x of n will be out of the differentiation because the base is z, so x of n has nothing to do with it. So we'll take x of n outside, then we will take the differentiation of z raised to minus n, which will be of course minus n into z raised to minus n minus 1. So we will simply put it here, and what we can do, we can take this minus symbol out, we can take this z inverse out as well. So by taking minus n and z inverse outside, we will be left with only these terms, n equals to summation of n equals to minus infinity to infinity and x of n z raised to minus n. And see, isn't it the same equation of z transform of z of z transform of n into x of n, right? So instead of that formula, we will write z into z transform of n of x of m, and the term which was multiplied earlier will remain as it is. So we will be left with this term, which was basically nothing but formula of minus z d by dz x of z, right? So hence we have proved that the z transform of n into x of n will be minus z d by dz x of z, and ROC is not changing whatsoever. Next one is your favorite convolution, which we have studied so many times. So, and again, for convolution you will require two signals, as we all know, we saw it earlier too. So we are having two signals, x1 of n and x2 of n, and the z transform of both of them is simultaneously x1 of z and x2 of z, with ROC for both of them simultaneously a1 between a1 and b1 point and between a2 and b2 point. So when we take both of these points x1 and x2, and when we take the convolution of it, the z transform of this cumulative signal will become x1 of z into x2 of z, and the ROC is intersection of ROC of x1 of z and x2 of z. So let's try to prove it. What will happen? We know what is the formula of convolution. Summation k is equals to minus infinity to infinity x1 of k x2 of n minus k. Now we have to take the z transform of it. So we will put this formula in under the formula of z transform. So we will let's say this formula convolution formula. So we will have summation n is equals to minus infinity to infinity convolution formula into z raised to minus n. Now we know that we can change the order whenever we have summation operation. So we will simply change the order for summation operation. So we will take this summation operation involving k variable outside, and the summation variable involving n variable will go inside the bracket. So what we will have summation k is equals to minus infinity to infinity x1 of k outside the bracket, and then inside the bracket we will have summation n equals to minus infinity to infinity x2 of n minus k into z raised to minus n. Now since we know from earlier time from time shifting property, we know that x2 of n minus k will be equal to z raised to minus k x2 of z. And see, somewhat similar thing is happening here. Somewhat similar case is happening here. We are having n minus k here. So what will be the Laplace of what will be the z transform of it? So it will be z raised to minus k x2 of z, and the remaining term k is equals to minus infinity to infinity x1 of k will remain as it is, and we can also call it z inverse k x2 of z, right? So we will call it x2 of z, and this z inverse k we can multiply it with this formula as well. So we will have summation k is equals to minus infinity to infinity x1 of k into z raised to minus k. Now again see this formula. This formula is basically the formula of x1 of z. So we have x1 of z, we have x2 of z, and we are getting the results, right? So hence we proved the convolution property as well. Now next one is the correlation of two sequences. And just like convolution, for correlation as well, you will need two different signals. So we are having two signals, n x1 of n and x2 of n. And when we take the z transform of both of them, we will get x1 of z into x1 of z and x2 of z. And the region of convergence for both of these signals are simultaneously a1. The region of convergence is from point a1 and b1 for x1 of z, and from point a2 to b2 for x2 of z. Now what does the correlation operation tells us? It says if we have signal x1 and n1, and if we delay my second signal or first signal or either of the signal by some value L, then the z transform, the change in the z transform will look something like this. See, I'm taking correlation, so summation n equals to minus infinity to infinity x1 of n, x2 of n minus L. So I'm taking subtraction here. So and I'm taking z transform of this signal, though, so the result will be x1 of z into x2 of z inverse here. Now it might be confusing for you, but let me clear it out for you. So we know the correlation formula. Basically this is nothing but the formula of correlation. So correlation for two sequences is given using this formula, n equals to minus infinity to infinity x1 of n, x2 of n minus L. Now what we can do is we can take summation n equals to minus infinity to infinity x1 of n, x2 of, instead of n minus L we can write it this way, minus L minus n. Thing is still the same, we are just changing the sign, but minus minus will become plus. So we can write it this way, we are not making any changes into the input. Then we can write x1 of L, and it will be in convolution with x2 of minus L. See, because this formula is basically becoming the formula of convolution. You can write it this way, right? And after that, what you can write, you can take the z transform of the whole signal, because we have to find the z transform after all. So let's take the z transform of this convolving function, and when we take the z transform of this convolution function, we know what will be the z transform of this convolution function, right? The z transform of this convolution function will be z of x1 of L into z of x2 of minus L. So the final z transform will be x1 of z into x2 of z inverse, because it was x2 of minus L, right? So we saw this earlier. So the final transform will look like this, and hence we proved the correlation property as well. Now let's see the next one. It is multiplication of two sequences, or you can also call it the z transform or convolution in the z domain. So what does the convolution in the z domain has to tell us? It tells us a different story, something new we will be facing here. It says if we are having two discrete time signals x1 of n and x2 of n, and if we take the z transform of both of them, and the z transforms are x1 of z and x2 of z, with ROC of between a1 and b1 for the first signal, and ROC of a2 between a2 and b2 for second signal, the multiplication of x1 of n and x2 of n. Okay, please note here, I'm not talking about the convolution here, I'm talking about multiplication of two signals, the multiplication of x1 of n and x2 of n. The z transform of multiplication of both of these signals will be 1 by 2 pi j summation of closed integral x1 of v, x2 of z divided by v into v inverse into dv. A little bit complexity here, but let me solve it for you. So here C is the closed contour or closed integral at, and it includes the origin and lies in the ROC which is common to both x1 of v and x2 of 1 divided by v. And because of that, the ROC is intersection of ROC of x1 of z and x2 of z. So that was the statement. Now see how we can prove it. So see, first we know what is the inverse Z transform, right? So the inverse Z transform basically gives us x of n, and it is equals to 1 upon 2 pi j close contours integration x of v raised to n minus 1 into dv. Now let's take multiplication of both of the discrete time signals first. So let's say x of n is equals to multiplication of x1 of n and x2 of n. And if we put this inverse Z transform of x1 of n in this equation, what we will get? You know what is the value of x of n, right? It is equals to 1 by 2 pi j close integral x1 of v raised to n minus 1 dv into x2 of n. Now let's take the Z transform of this whole term, right? The whole x of n. So the whole x of n will be written here into multiplied with z raised to minus n, and the whole term will be under the summation of n equals to minus infinity to infinity. Basic Z transform formula. Now let's interchange the order of integration and summation. We can do that because it is basically integration and summation, so we can change the order, right? So first let's take the constant value outside the both integration and summation. So let's take 1 by 2 pi j outside the integration and summation. Now let's take integration first, and then inside of it we will put the summation. By that we will be simplifying the solution. So we can take the integration outside. So close integration x1 of v will be outside, and we will taking the summation n equals to minus infinity to infinity v raised to n into v raised to minus 1. Instead of v raised to n minus 1, we can write it this way as well: v raised to n into v raised to minus 1 x2 of n z raised to minus n into dv. So we are simply taking the first term outside and the constant term outside. We are keeping the other terms as it is, but inside the summation. Now if I take this v inverse outside of my bracket, outside the summation, so isn't the inside of it looks familiar to you? The term inside the bracket n equals to minus infinity to infinity x2 of n z divided by v raised to minus n. Remember the time scaling property, right? It holds resemblance with it. So it is nothing but the Z transform of x2 z by v, the basic time shifting property we saw earlier in this class only. So this is it, simply it is. And then the other term will be 1 by 2 pi j in the closed integration x1 of v, and the other term will be x2 of z divided by v into v inverse into dv. So this term is the same as this term, see, and hence we have proved the multiplication property of two sequences or the convolution operation in Z domain. Now let's see next property, which is conjugation of complex sequences. In this we are simply going to take the conjugate of my original sequence, conjugate of my original signal. So if I'm having a signal x of n and its Z transform is x of z with region of convergence between points r1 and r2, then what will happen to if I take the conjugate of my base signal x of n? It will be x conjugate of n, and the Z transform will be x conjugate of z conjugate, right? This one is a bit tricky, but let's see what happens. let's take the Z transform of X conjugate first. So the Z transform of X conjugate will look like summation n equals to minus infinity to infinity X conjugate of n into Z raised to minus n, which will be basically equal to summation n equals to minus infinity to infinity x of n Z conjugate raised to minus n and raised to the whole conjugate. So we are not doing any change into my base form here, right? We are taking two conjugates, which means we are not changing anything. So instead of this, what we can do, we can take the conjugate of the whole term, and that's what we exactly did. Now see the term inside the bracket here. Isn't it the Z transform of x of z conjugate? So it is basically Z transform of x of z conjugate, but as it is a Z transform of x of conjugate, and as it is having conjugate here as well, so the term will be x of z conjugate and the conjugate of it as well. And when we are having two conjugate, we break this bracket, so we will have x conjugate into the z conjugate, right? So it is same as this one. So hence your conjugate of complex sequence has been also fulfilled. Next one, the 10th property is the Z transform of real part of a sequence. So we are here taking a sequence and we are taking the Z transform of real part only. So imagine I'm having a signal which is x of n, and when I take the Z transform of it, I will get x of z with region of convergence between point r1 and r2. Now what I will do, I will take only the real part of this signal. Okay, x of n is a complex signal, so I'm taking the only the real part from my signal, and I'm taking Z transform of that only real part. Now who remembers the even and odd signals? What was the formula to find out the even component and odd component, right? If you remember, here you are having your answers. So when you take the Z transform of real part of your complex sequence or complex signal, the Z transform will be 1 by 2 x of z plus x of z conjugate into z conjugate. How? Let's see. I'm having x of n, which is complex number, which means it will have real and imaginary values, as you can see here, and the conjugate of it will be opposed, will also have real and imaginary values, but the sign of imaginary value will toggle, will change. If I'm having positive value here, so I will have negative value here. So this is my conjugate signal, x conjugate of n, right? And the real part, so the real part will be 1/2 x of n plus x conjugate of n, right? Now let's take the Z transform of this real part, and when I take the Z transform of this real part, what will happen? Basically this 1 by 2 can be thrown out outside the bracket, so we can throw this 1 by 2 outside the bracket. We will have z raised to Z transform of x of n and Z transform of x conjugate of n. Now the Z transform of my x of n will be x of z basic, right? And in the previous property only we saw the Z transform of x conjugate of n will be x conjugate of z conjugate. So it will be x conjugate of z conjugate, and that is your answer, right? Hence we have proved the Z transform of real part of a sequence. Now let's see for the imaginary part. We can also see the imaginary part as well. So what is the Z transform of imaginary part of sequence here? So we'll do the same. Instead of plus, we will have minus here. Here we had plus, so we will have minus. Instead of this 1 by 2, we will have 1 by 2j, because it is a complex number and it is imaginary part. So we will have j multiplied with it. So whenever we take the Z transform of the imaginary part of my complex variable or complex signal, the Z transform of it will be 1 by 2j x of z minus x conjugate of z conjugate. And let's do the same thing with which we do with real component. We will take the Z transform of imaginary component again. So when we take the Z transform of imaginary component, what we can do, Z transform of 1 by 2j x of n minus x conjugate of n, and we can say that 1 by 2j uh, x of n minus Z transform. Basically we are multiplying this Z transform inside the bracket, and you know what is the value of x of n, so we will have x of z here, and you also know what is the value of Z transform of x conjugate of n. It is x conjugate into z conjugate. We saw it in earlier property, so it is basic same. If you know the Z transform of real value or real part, then you can also find the Z transform of imaginary part very easily. The next one is the Percival's theorem. This is very popular and a lot of people ask it in the some examinations as well. So a little bit tricky, but I think you will get the hold of it. Not that much tricky. Let's see what does it do. So let's say we are having two signals x1 of n and x2 of n, and the Z transform of both of these signals respectively is x1 of z and x2 of z. Now Percival's relation tells us that if I'm having if I'm having summation of n equals to minus infinity to infinity, x1 of n, x2 conjugate of n, it will be equal to 1 by 2 pi j closed integration x1 of v, x2 conjugate of 1 by v conjugate into v inverse into dv. Now this property is also a little bit familiar property which we saw earlier. It has resemblance with that property of multiplication. So let's see what will happen with Percival's relation, right? So see, let's take the inverse transform of x1 of z. My x1 of n is equals to 1 by 2 pi j in closed integral x1 of v raised to n minus 1 into dv. Now what we will do, we will take the summation of n equals to minus infinity to infinity x1 of n into x2 conjugate of n, and we saw it from earlier property. What is the value of it? Its value is equals to its value is summation of n equals to minus infinity to infinity 1 by 2 pi j closed integral of c x1 of v raised to n minus 1 dv into x2 conjugate. Now what we can do, we can do the same thing we did earlier. We will this time we will take constant value outside the summation and integration. We will change the order of summation and integration one more time. This time we will send summation inside inside and outside. We will keep integration just like we did last time. We will keep x1 of v with integration just like we did last time, and the rest of the term will form the equation of c. Summation of n equals to minus infinity to infinity x2 conjugate of n v raised to n minus 1 into dv. So here we know instead of v raised to n minus 1, we can write v raised to minus 1 into v raised to minus n. Sorry, v raised to n into v raised to minus 1. And it will be equal to 1 by v raised to minus n, right? We can write it instead of v raised to n, we can write 1 by v raised to minus n into v inverse. And if we do that, see, because what is v raised to n minus 1? V raised to n minus 1 is basically v raised to n into v raised to minus 1. So we are keeping v raised to minus 1 as it is, but we don't want v raised to n. We want negative value. We want something raised to minus n. So if I want minus n here, what I have to do? We have to take 1 upon v raised to minus n, right? So 1 by v raised to minus n into v inverse. When we take it, we can write this equation this way. All the term outside the bracket will remain as it is. There will be only change in v raised to n minus 1. Instead of v raised to n minus 1, we will be writing 1 by v raised to minus n into v inverse. Now what we can do, we can take the v inverse outside the bracket. So the term which will remain inside the bracket will be summation n equals to minus infinity to infinity x2 of n into c. We are removing this conjugate from x2 and we are putting it on v. Why, you will understand when we get done with it. So we will be left with 1 divided by v conjugate into minus n, the whole conjugate of the thing. So now you understand, we are not basically removing this conjugate from here, we are taking conjugate of whole term. So when we take the conjugate of this whole term, so what will happen? This conjugate and that conjugate will cancel each other out, you can say, or you can say that we are removing this conjugate and we are taking the conjugate here. So this term will get conjugate because it didn't had earlier. This time what will happen? Next step, the outside the bracket situation will remain as it is, but see this formula, it is same formula as we see earlier, right? Scaling property. So we are having x2 of 1 by v conjugate into the whole conjugate, and you know what is the value of this whole term? We saw it in previous property as well. So it is nothing but the Z transform of x2 of 1 by v conjugate, and the remaining terms v inverse into dv remains as it is. X2 conjugate, because of this conjugate we will get x2 conjugate, x1 of v remain as it is, and the other term outside the whole integration and summation will remain as it is. And when you compare this term with the term of my Parseval's reaction, Parseval's relation basically, so both the terms are same, see, and hence you've just proved the Parseval's reaction or Parseval's relation as well. The last property of today's class is initial value theorem, and we have seen initial value theorem earlier as well. So let's see one more time with in regard of Z transform this time. So let's say I'm having a signal x of n, and when I take the Z transform of my signal, so the Z transform will be x of z. Now what does initial value theorem tells us? The value of x of 0 will be equal to the limit z tends to infinity of x of z. Now you might don't know this, you will know when we discuss about the causal integration of Z transform, but the Z transform of causal sequence can be given using this formula. X of z equals to summation n equals to 0 to infinity x of n z raised to minus n. You know that this is the formula of basic Z transform. Since x of n equals to 0 for n less than 0, you can also expand it this way, right? For all the values of n less than 0, your x of n is 0. So you are only having positive values and 0. So you can write x of 0 raised to z raised to 0. Z raised to 0 is basically 1. X of 1 raised to z raised to minus 1. So it will be x of 1 z inverse plus x of 2 z raised to minus 2 plus x of 3 z raised to minus 3, and up to it will go till infinity. Because your signal is getting integrated or not integrated, added or summed from 0 to infinity. Now let's apply the limit because it is the demand of the initial value theorem. So when we apply the limit, what we will get? The limit will be limit x of z, z tends to infinity, and we will apply the limit on every single element of my signal. So you will have limit x of 0, z tends to infinity, plus limit x of 1 z inverse x tends to infinity, plus limit x of 2 z raised to minus 2 z tends to infinity, up to it will go till infinity. And remember, when we have z tends to 0, whenever we have anything tends to 0, its value is always 0 inside the limit, right? So except of x of 0, because it is not having value z inside of it, so except of x of 0, all the rest of the values will become 0. So only thing you will be left with be x of 0, right? And what is the what is the value of x of 0? It will be equal to limit z tends to infinity x of z, the term on the left side. So we just exchange the term on the left hand side and right hand side, and hence you have proved your initial value theorem as well. So we will keep today's class till here. If you are having any doubts, any confusion with this class, you can mention your doubts in the comment section below. If you have any suggestion for the channel or the way of representation, you can mention that in the comment section below as well. I will be seeing you next time with a new topic regarding Z transform. Till then, take care of yourselves. Goodbye and thank you very much for listening.